We've established that light is just one of many forms of electromagnetic radiation that exist in our universe. But where exactly does light come from? How do we use it practically in our everyday lives and in our chemical experiments? I'm going to introduce the three main sources of light, and then we're going to go all in on one of those sources in this video and the next video. So let's begin. What do you think of when you think of light? Pause and think for a minute. Maybe it's a light bulb, or maybe it's the sun. Both of these are sources of white light, and the white light comes from the fact that the light encompasses all of the wavelengths that are in the visible spectrum, and so when they mix, we end up with white. But if you took an instrument called a spectroscope, which generates a line to represent each individual wavelength of light that is observed, you would see a smear, because many different and indistinct light wavelengths exist in the white light. This is in direct contrast to the second type of light source, which are sources that emit only one specific wavelength of light, like an LED light or a laser pointer. Red laser pointers typically release light with a wavelength of around 650 nanometers. In this case, there's only a single wavelength released, and what you see is what you get. And if you used a spectroscope to look at these sources, you would see a single line corresponding to the single wavelength of light that is emitted from the laser pointer. So, what's the third source? The third source are actually atoms themselves through a phenomenon called atomic emission. What do I mean by atomic emission? Let's take a step back and look at the electron configuration of hydrogen. Let's draw it out. Hydrogen has an electron configuration of 1s1. This is the ground state electron configuration, which means that when you have hydrogen just hanging out under normal relaxing configurations, the electron diagram looks like this, with one electron hanging out in the 1s orbital. Now, let's say that energy, either in the form of visible light or UV rays or some other wavelength, is shown on our hydrogen atom. And the energy of that incoming light just happens to be equal to the energy difference between the 1s orbital and the 2s orbital. When this happens, the electron absorbs a photon from the incoming light, and now it is a higher energy than it was before. The energy change associated with this change is positive, as the electron has increased in energy and the energy is being taken into the system. We call this the excited state, this higher energy state, the excited state of an electron, and the process of the hydrogen mopping up a photon is called absorption. And it's the same absorption that we just talked about in the particle video. But will the electron hang out in the 2s orbital forever? No. So eventually that electron has to fall back to the ground state. So when this happens though, for the electron to have its old original lower energy, the electron will release that same photon back out to the surroundings. And that photon has an energy equal to the energy difference between the 1s and 2s orbitals. The energy change associated with this transition is negative because the electron is losing energy, but also because the photon is released away from the perspective of our system. We call this process the emission of a photon. And this is the genesis of the light source of atomic emission, where we see lights that are emitted from atoms. Now, how do we know that the energy of a photon will be equal to the energy difference between the two states of an electron? This is because of a concept called quantization. Do you remember back when you learned how to draw electron configurations? The electron could only go into the specific circles that represented particular orbitals. You couldn't just draw the electrons anywhere, like between orbitals or half in one or off in space. You couldn't invent your own orbitals. Kind of like rungs on a ladder, the electron had to hang out in a particular slot, not between the slots. If you step between the slot, you fall through the ladder and fall over, and it's bad luck. Same thing for electrons. Similarly, for an electron to move, it has to absorb the very specific amount of energy that will correspond with the energy jump to a particular orbital or n level. Photons that have more or less energy than is needed for a particular transition will be passed through or will reflect off of the surface of the atom. Another way of thinking about this is that the substance, or our atom specifically, will reject photons that don't match an energy gap that the electron can take to be promoted to a higher energy. And if you have an atom is going to have multiple of these transitions. And the sum of these electrons that are being rejected or that are being released from the atom gives a distinctive color that we refer to as atomic emission. So now that we've learned about light sources and jumping electrons, how do we tie emission into light sources, specifically for a particular atom? Well, we've got one more video for that, so stay tuned.